Hello students, good morning to all. I am Rao Sharma from LPM School, Gola Gorakhpur. Today I am going to take lecture of 12th class. As you know, this is your physics lecture. The chapter electric charge and field is going on. In previous class, I have discussed about the Gauss theorem. So today I am going to discuss about the application of Gauss theorem. This is very important for your exam and solve numerical problem also. So first I am going to solve the first application, electric field intensity. Electric field intensity due to an infinity long wire. It means we have to find the electric field intensity due to an infinity long wire. So let an infinity long wire that this is a wire and this is infinity long. Electric intensity for a long straight infinity long wire, and this is a charged wire. So you can add charged infinity wire. Okay, so is charged by positive charge. You can solve with a negative charge, there is no problem. So let this is a wire consists positive charge, and we have to find intensity at point P. Let this is point P where we have to find intensity, or you can say the strength of the electric field. So as you know, the Gauss theorem works for a closed surface. The Gauss theorem will work only for a closed surface. So this is a infinity long wire. So to enclose this portion of this wire, so draw an imaginary surface. Let an imaginary surface. The portion, the small portion of this surface is enclosed. Let the length of this portion is L. So you can say the length of this imaginary surface, and this imaginary surface is cylindrical. So you can say this is an imaginary cylindrical surface, and it is known as Gaussian surface. So it is an imaginary surface, this is known as Gaussian surface, to enclose any charge. So the length of this Gaussian surface is L, and the radius is R. R is the distance of point P from wire. So you can write radius of imaginary Gaussian surface equal to R. Length of Gaussian surface and this is cylindrical. This is L. This question you can write. This is an cylindrical Gaussian surface. Cylindrical Gaussian surface. This is cylindrical Gaussian surface. So radius is R and length is L. And the surface, this is a wire. So it consists only one dimension. So the charge distribution is linear. So linear charge density. Lambda, linear charge density, linear charge density equal to lambda, and let the charge enclosed by this portion is q. This is q charge enclosed by the mineral Gaussian surface. So lambda equal to q upon L. So value of q is equal to lambda L. So this is the theory. You have to draw this diagram and you have to write this theory. Now the flux, electric flux related to this Gaussian surface. Electric flux linked with cylindrical Gaussian surface phi equal to, this phi is equal to the total flux linked with the Gaussian surface. So before find the flux, we can resolve the total portion, the total surface of this Gaussian surface into three parts. Like this is first part, second and the third. The first portion of this cylindrical surface is the top. This is a cylinder. So this is top, first surface, and this is curved surface area of this cylinder. This is second portion, and this is bottom. This is the third surface area related to this cylindrical surface. So total flux is given by the algebraic sum of total flux. Total flux phi equal to the sum of individual flux related to all these surfaces. It means the phi equal to flux for first surface, flux linked with first surface. It means you can say this is phi 1. Second, the flux linked with second curved surface. This is curved surface. So this is phi 2. And flux linked with third surface. So this is phi third. Now the phi E, electric flux, phi E dot ds. This is not closed surface. This is flux related to first surface. Now flux related to second surface. Flux related to third surface. Now the first surface for toe, the electric field lines, as you know, the electric field lines emerge normally between the electric field lines like this, normal to the surface. This is electric field line emerges from positive charge, this wire, and this is wire. So then electric field lines are like this, normal to the surface. This is the direction of electric field line. And the area vector related to the toe. This is the toe. So for electric, this area vector is normal to the surface. So this is, as you can see, if this is a cylindrical surface, this is toe, so electric area vector are normally to the plane. This is plane, then area vector is normal to the plane. So this is the direction of area vector. So you can see clearly the 90-degree angle between electric field lines and area vector. For bottom, it is similar. This is electric field line and this is area vector, 90 degree. But for curved surface area, the direction of electric field line is outward to the curved surface area, and the surface area is, and the area vector is, that this is S. You can write A, but use S, so use S. You can write A, there is no problem. So ds, this is also ds, and this is ds. So as you can see, electric field line and area vector are parallel, it means in same direction. So theta is equal to 0. So E ds cos 90 for first surface, second E ds cos 0 for second surface, and E ds cos 90. So I hope you understand. So value of cos 90 is 0. So it means flux linked with this portion is 0. The value of cos 0 is 1. So E ds cos 0 is 1. And flux linked with bottom is also 0, because cos 90 is also 0. So total flux is given by only the curved surface area. Okay, now we have to solve this. So phi E equal to E common ds, and the curved surface area of a cylinder, as you know, it is equal to 2 pi r L, 2 pi r h and h equal to L, so 2 pi r L. 2 pi r L. Equation first. By using Gauss theorem, and by putting the value of charge, and this is equal to lambda L. Equation first. By comparing equation first and equation second, E 2 pi r L equal to L upon epsilon. Lambda cancel. E equal to 1 upon 2 pi epsilon naught lambda upon r. This is the value of electric field intensity for a infinity long charged wire. 2 pi epsilon naught. You can write E equal to 1 upon 4 pi epsilon naught by multiplying and divide by 2. Okay, so I hope you understood about how to solve, how to find the electric field intensity due to a infinity long charged wire. And you can write the vector form of this. E equal to 1 upon 4 pi epsilon naught 2 r upon r is the distance and r cap. This is the vector form. So I hope you understand how to find the electric field intensity due to a infinity long charged wire. This is very important derivation, and this is very important for your board exam, and numerical also will come based on this formula. Okay, so I hope you understood how to solve the first application of Gauss theorem. Now in my second video I will explain the second application of Gauss theorem. So thank you very much. You can take this screenshot or you can note down in your notebook. This is very important.